So welcome dear learners in course Maintenance and Testing of Electrical Machine week 6 lecture number 3, and today we will discuss about the various types of DC machine and its application and how this DC machine is selected, and also we will see some of the important numerical problems which are associated with this DC machine. So let us see different types of DC motors and its application with respect to the different characteristics of DC motors. So the first motor is the separately excited DC motor. So in this particular motor, very accurate speed can be obtained by those motor. Moreover, those motor are the best suited where the speed variation is required from very low value to very high value. Those motor are used in steel rolling mill, paper mill, diesel electric propulsion of ships, etc. The torque speed characteristic of DC motor are very important to understand for controlling and designing of a system that uses those motor. Okay, so we will see the DC shunt motor and its different application. Let us understand the speed torque characteristic of DC shunt motor. In a DC shunt motor, the speed remains relatively constant with varying torque or load, we can say. Okay, so it means load is the speed is almost constant with respect to the change in load. Okay, now we will see the torque. As torque increases, speed slightly decreases, as I already mentioned. What about speed? The speed is nearly constant because field current remains relatively unchanged due to the shunt configuration, and the back EMF, which opposes the supply voltage, balances the armature current. So in the case of DC shunt motor, the back EMF is balancing the armature current in order to get the almost constant speed. So these characteristics makes DC shunt motor suitable for application which requires constant speed, such as conveyor belt and elevators. Okay, and if you see the graph of characteristic graph of a DC shunt motor, then if you see the speed torque curve of a DC shunt motor, then it is almost flat, which indicate a little change in the speed with respect to the change in torque. Okay, so let us see what are the different applications of the DC shunt motor. It has been extensively used in the blower and fan application. Okay, and it is also used in the centrifugal and reciprocating pumps, and it has been exclusively used in the lathe machines where the constant speed is required. Also, it is used in the machine tools, milling machine and drilling machine. So these are some important application of a DC shunt motor. Now let us see the DC series motor. In DC series motor, the field winding is connected in series with the armature. It is a configuration of the DC machine. Now we will see the speed torque characteristic. In a DC series motor, a speed decreases sharply as torque increases. Which means whenever we are increasing the torque, there is a sharp decrement in the speed. Okay, now let us understand about the torque. The torque is high at very low speed and decreases as speed increases. Let us see the speed. At no load condition, the speed can be increased to a dangerous level, but as load increases and torque decreases, the speed drops significantly. Therefore, this characteristics makes DC motor is ideal for application where we require a high starting torque, such as electric train and cranes, where we require a very high initial torque. If we talk about the speed torque curve of a DC motor is highly nonlinear, which means a steep slope indicating a large decrement in the speed with respect to the increment in the torque. And due to this particular characteristic, these DC series motors are exclusively used in the cranes, hoist and elevators, trolley and conveyor systems. Also it is used in the electric locomotive. There is an important note for the DC series motor, which is a DC series motor always directly coupled with a load or coupled through a gear. Okay, belt loads are never applied to the belt loads are never applied to the DC series motor, because belt may be slipped over to the pulley or it may break. Then the motor will operate at light load, and at no load will attain dangerously high speed, which may damage to the motor. Okay, so always we connect the DC series motor with some gear mechanism, or directly we connect to the load. Now let us see about the DC compound motor. DC compound motors combine both the winding, series and shunt, and depending upon their position we are having the long shunt compound motor and short shunt compound motor. Okay, so let us see the speed torque characteristic of a compound motor. The characteristic of compound motor falls between that of a shunt motor and a series motor. It provides good starting torque due to the series winding and relatively stable speed due to the shunt winding. And if you talk about the speed torque curve, then it is a mix of then this characteristics is the mix of characteristic of shunt and characteristic of series motors, which moderate speed variation as torque changes. And because of this particular characteristic, this compound motor is exclusively used in the rolling mill operation, punches, shearing, heavy planers and elevators. Okay, now let us see about the differentially compound. Speed increases as load increases. So definitely there is no practical application of a DC compound. Let us understand the selection of DC motor. While selecting a DC motor for a particular work, one is to consider following points. The first important point is the selection of power rating. If the size, which means HP power rating, horsepower rating or kilowatt capacity of the motor, is more than the load to be picked up by it, then it will be operate at lighter load condition than its rating. Hence, there will be a more losses, motor will operate at poor efficiency and unnecessarily there will be a wastage of power. Therefore, extra expenditure will incur during operation. At the same time, initial cost will be high because we have selected the overrated motor for a particular application. Okay, so whenever you are selecting a motor which is higher than the rated capacity required by the load, then expenditure and losses will be more. And on other hand, if the size of the motor is less than the load to be picked up by it, then it will be overloaded and it will be heated up beyond its limit. Hence, the motor may be damaged if operated continuously. Otherwise, also protective devices will disconnect the motor under overload condition, and this will affect the whole production cycle. Thus, a motor should be chosen a size for the maximum power utilization. During operation, it should be heated up within the permissible temperature limit and it should never be overheated. But at the same time, it should be capable of handling the overloads for the temporary. But at the same time, it should be able to take up the overloads temporarily. Now, let us see the characteristic of the motor. For satisfactory operation, the selection of power rating of a motor is not only a criteria, but rather should be For satisfactory operation, the selection of power rating of a motor is not only criteria. Rather, one should know the characteristic of a motor, behavior of motor under different load condition, so that work can be done quickly and efficiently without any breakdown. Therefore, before selection of a motor, one should know the following particular of the work. The first point is the torque requirement during starting and running at different loads. It is very important for any particular application. Requirement of accelerating and braking torque. So accelerating torque and braking torque with respect to the load is very important if you are selecting a particular motor. Frequency of switching. Frequency of switching means how often you are changing the load, okay, from the no load to the full load, that is required. The next one is the temperature of the workplace. Temperature of the workplace means the place where the motor is actually placed. So depending upon the indoor and outdoor application, the temperature may vary. And next point is the environmental condition. Again, where we have put the motor, like there are n number of application of the motor. So where it is a what we call the very rough and tough environment in the like industry, or a very delicate environment like air conditioning application. So depending upon the what we call the environmental condition, we have to select the motor and its outer body, which is commonly known as enclosures. So after knowing above particulars, a workplace, a suitable motor will be chosen to meet those criteria. To understand the practical perspective of a DC motor and DC machine, the numerical problems are very much necessary. So we will see some of the important numerical problems which are associated with the DC machine. So let us see the first numerical problem, which states that an 8-pole lap wound DC generator has 960 conductors, a flux of 40 milliweber per pole, and driven at 400 rpm. Find the open circuit EMF. So in this particular problem, we have to find out the EMF, the value of EMF generated in the generated at the armature end, okay. And we have like whenever you are solving any numerical problem, the first step is to find out what are the values are given. The first value is given is the 8 pole. 8 pole means the total number of pole is 8, okay. The second value is given is the total number of conductor. So Z is equal to 960, okay. And the next value is given in the particular question is the flux per pole, which is 40 milliweber, okay, and speed is 400 rpm. So these values are given, and we have to find out the open circuit EMF. So open circuit EMF is nothing but a induced EMF in the DC generator when there is no load is connected. So as we know the formula of EMF generated, which is P phi NZ upon 60A. Put the value of flux per pole, flux, number of poles, put the value of P phi and NZ and A, where A means A is the number of parallel path. Since it is a lap winding, so A is equal to P, which means A is equal to 8. So put those values in the formula. So then what you will get? You will get the value of induced EMF, which is 256 volt. So this value will be induced in the generator. So it is a very pretty much easy problem, because we have obtained the induced EMF in a single stage. Now we will see one more problem associated with this induced EMF, okay. So let us solve the numerical problem number 2, which states that a 4-pole DC machines has 144 slots in the armature with two coil sides per slot. Each coil has 2 turns and flux per pole is 20 milliweber. Armature is lap wound and armature is rotating at 720 rpm. What is the induced EMF? First across the armature and second across the parallel path. So let us solve this problem. So in this particular problem, number of poles is given as 4. Number of parallel path A is equal to P, because it is a lap wound machine, which means A is equal to 4. Flux per pole phi is equal to 20 milliweber, and the RPM is 720 RPM, okay. So here we have to find out the value of Z, because Z is not directly given. So Z is equal to what? Here what it is state that it has a 144 slots in the armature with 2 coil sides per slot, which means 144 into 2 into 2, which means what you will get the value of Z, which is equal to 576 total number of conductors. Okay, now we will easily find out the value of induced EMF across the armature. Eg is equal to P 500 upon 60A. Put all the values are given. Then finally what you will get, you will obtain the value of induced EMF across the armature, which is 138.24 volt. It is the first case. Second case, what we need to find out? We need to find out the induced EMF across each parallel path. So induced EMF across each parallel path is nothing but a induced EMF across the armature only. So which means voltage across each parallel path is equal to 138.24 volt only. Okay, so this is the tricky question, like we have to solve the we have to obtain the induced EMF in two different cases. However, those two different cases are same only. Okay, now let us see the next problem, which states that a 6-pole machine has an armature with 90 slots and 8 conductor per slot. The flux per pole is 0.05 Weber and RPM is 1000 RPM. Okay, so we have to determine the induced EMF in the winding when it is connected in a lap wound and when it is connected in a wave wound. So there are two different cases where we have to find out the value of induced EMF. Let us take the first case when the machine is connected in the lap wound configuration. Okay, so here P is equal to 6, phi is equal to 0.05 Weber, N is equal to 1000 RPM, number of slots is equal to 90, each slot with 8 conductors, which means Z is equal to 90 into 8, which means 720 is the total number of conductor. Put those values in the first case when A is equal to P, which is equal to 6. Okay, so substituting those values, you will obtain the induced EMF as 600 volt. Now same machine is reconfigured for the wave winding. Now if you substitute those values except A is equal to 2, then what you will obtain? You will obtain induced EMF for the wave connected armature winding is 1800 volt. So as you can see, when a machine is connected in a wave winding and when machine is connected in the lap winding, there is a change in the induced EMF just because of A. Here the induced EMF is increased as the machine is changed in its configuration from lap wound to the wave wound. So there is an increment in the induced EMF. So you will get some kind of objective question whenever there is a change in the configuration of a DC machine from the lap wound to wave wound, then what will be the effect on the induced EMF? And no doubt induced EMF will be increased considering all other parameters are still same. Okay, so in this way you can understand the numerical problem. Okay, now let us see some bit difficult numerical problem, which states that the EMF generated by a 4-pole DC generator is 400 volt when armature is driven at 1200 RPM. Calculate the flux per pole if wave wound generator has 39 slots having 16 conductors per slot. This is the statement of the question. Now we will see what are the given values. So in this particular question, number of poles P is equal to 4 is given, Eg is given, which is induced EMF is 400 volt, RPM is given as 1200 volt, and total number of conductors Z is equal to 39 into 16, which is equal to 624 is given, and since it is a wave winding, which means A is equal to 2. Now first we need to find out the flux per pole. So if you reconfigure the formula of rearrange the formula of induced EMF, what you will get? You will get the phi is equal to Eg into 60A upon Z into N into P. So put the value of known values, then what you will get? You will get flux per pole as 16 milliweber. Okay, so here by rearranging the formula of induced EMF, we have obtained the flux per pole. Now let us see the one more numerical problem which is associated with the DC generator. A 4-pole wave wound DC generator has 51 slots on its armature and each slot had 24 conductors, and the flux per pole is 0.01 Weber. At what speed the armature must rotate so that the induced EMF will be 220 volt? What will be the EMF developed if winding is lap connected and armature is rotated at the same speed? So here we are having two different conditions, and in two different conditions we have to find out the value of speed and the induced EMF. So let us solve one by one. So as we know, the formula of induced EMF is nothing but a P phi Az upon 60A. Now let us see what values are given. So here phi is given as 0.01 Weber. This total number of conductors is not given directly. So Z is equal to 51 into 24, because this machine has 51 slots and each slots having 24 conductors. So 51 into 24, which is nothing but 1224. And induced EMF is 220 volt is given in the first case when it is wave wound. Okay, and in the case of wave wound, the A is equal to 2, and since it is a 4-pole machine, so P is equal to 4. Substituting those values in the formula of induced EMF, you will get the speed. So what speed you will get? You will get the speed as 539.21 RPM. So which is closely equal to the 539 RPM. Okay. Now this machine is reconfigured for the lap winding. So in the case of lap winding, A is equal to P. Okay, so A is equal to P, which means A is equal to 4. So substitute those values in the basic EMF equation, then what you will get? You will get the value of induced EMF. Okay, so in the case of lap winding with the same speed, what you will get? You will get the induced EMF as 110, which was earlier as 220 volt. So as you can see, when speed is taken as when speed is same as first case, then in the second case you will get the reduced induced EMF. So in this way you can solve the different problems. Okay. So in this particular lecture, we have seen the different applications of the DC machine with respect to the different characteristic of the DC machine. Okay, and we have also seen how we can select a DC machine for a particular application. We have seen the different criteria for them, and at the end we have solved some of the important numerical problems which are associated with the induced EMF, torque equation and other related formulas. So thank you so much, listeners.